What if the smallest things you have ever imagined are not made of anything at all, but instead are gentle ripples in a deeper, invisible sea that surrounds you even now? And if this quiet journey draws you in, if these explorations of the cosmos offer you even a moment of calm, feel free to tap like or subscribe only if it feels natural and true to you. As you settle into the stillness around you, imagine the familiar world softening at its edges. The lamp beside you, the walls around you, the quiet weight of your own body. All of it seems so solid. And yet everything you touch, everything you see, is built from electrons drifting in vast, silent orbits. Tiny, ancient, unbroken. Tonight, you and I are going to follow a single one of them. Not rushing, not pushing forward, but drifting inward as though descending through layers of meaning, layers of scale, into a realm where even the idea of inside begins to dissolve. We begin with a whisper of history, because the story of the electron is not only scientific, it is deeply human. Over a century ago, J.J. Thomson watched strange threads of light curl and bend through a glass tube. Cathode rays, as they were called then, flickered like glowing threads in the dark. No one knew what they were made of, but Thomson measured how those rays curved in electric and magnetic fields, and realized they carried the same tiny charge over and over. Something universal. Something smaller than anything science had ever touched before. The first fundamental particle ever discovered. A particle that would reshape our understanding of atoms, electricity, chemistry, and the structure of matter itself. But even then, no one truly understood what it was. You breathe quietly now, letting your mind drift. Those early rays of light narrow in your imagination, shrinking and shrinking until they become a single wandering mote. Decades pass, and experiments sharpen. By the late 1960s, physicists at the Stanford Linear Accelerator Center fired beams of electrons at protons with energies so high they shattered open the proton's interior, revealing the quarks inside. When the same technique was turned toward the electron, searching for cracks or granules or hidden structure, the universe answered with silence. The electron behaved like a perfect point. No internal landscape, no smaller parts, no shell to break. Later, the Large Hadron Collider would push these tests even further, searching for signs that electrons might be made of something deeper. But again, the results showed no deviation. Down to distances far smaller than any atom, far smaller than any nucleus, the electron still appeared structureless. Physicists usually describe this scale by saying the electron looks point-like down to distances around 10 to the negative 19 meters. For the sake of clarity here, imagine this instead. If an atom were scaled up to the size of an entire planet, the region in which the Oz electron still shows no structure would be smaller than a single grain of dust drifting somewhere above its ocean. And yet the electron has mass. It has charge. It has spin. An intrinsic angular momentum that is not a literal rotation, because something with no size cannot spin in the usual sense. It interacts. It shapes the world. It builds every molecule in your body. How can something without an inside carry so many properties? You sink deeper into this question, drifting into the quiet territory where quantum field theory lives. Here, the world is not built from little spheres and beads. It is built from fields that stretch across all of space, smooth and continuous, humming with a faint secret energy even in total darkness. The electron is not a tiny object floating in a void. It is a vibration, an excitation of the electron field. Wherever this field trembles in a particular way, we say an electron exists. Its mass, its charge, its spin. These are not stored inside it. They arise from how the field interacts with space-time itself. Picture the surface of a calm lake at night. A single ripple moves outward. The ripple is not a separate thing. It is the behavior of the water beneath it. In this quiet image, the electron is the ripple. The electron field is the lake, and space-time is the softly breathing world around it, holding everything in place. Richard Feynman, exploring this world, discovered that an electron's motion is shaped by every possible path it could take. Empty space, he found, is not empty at all. Virtual particles appear and vanish, flickering through the vacuum, nudging the electron in ways so delicate that only the most precise experiments can reveal them. And reveal them they did. Experiments using penning traps captured single electrons, suspended them in magnetic fields, and measured their magnetic moment with staggering accuracy, better than 1 part in a trillion. The results matched the predictions of quantum electrodynamics almost perfectly, as though the universe itself were whispering that this understanding is true. The deeper you drift, the more the idea of smaller begins to unravel. Physicists speak of a boundary called the Planck length, a scale so tiny that the very concept of distance may lose meaning. If space cannot be divided beyond that scale, then the question of what lies inside an electron becomes not a physical question, but a poetic one. The universe answers gently. An electron is itself, a fundamental rhythm in the quiet fabric of reality, not built from smaller things, not hollow, not solid, more like a note than a particle, a vibration that has existed since the earliest moments after the Big Bang. Let this idea settle for a moment, like dust drifting through a sunbeam. Everything around you, the firmness of the mattress beneath you, the stillness of the air, the shape of your own body, comes from the soft language of electrons. When you touch a wall or place your hand on your chest, you are not feeling matter pressing against matter. You are feeling the quiet tension between electron fields, gently repelling one another. Solidity is a sensation born from distances that never truly vanish. And in this calm truth lies something strangely comforting. If the world is built from things that have no inside, then you too are woven from patterns rather than pieces, from resonances rather than objects, from ancient vibrations that stretch across the universe, shaping stars, molecules, and moments in equal measure. The electron carries many mysteries, but not the mystery of hidden structure. Its deepest truth is simpler, more subtle, more profound, that something so small, so empty of pieces, can still give rise to everything you know. And as this thought settles into the quiet spaces of your mind, another question begins to form, soft as a distant shoreline, calling you gently onward. And as that shoreline grows clearer in your imagination, you drift toward it with the same slow steadiness that an electron shows as it moves through space, guided not by a path, but by a probability wave that spreads softly in all directions. You stay with that sensation for a moment, letting the idea breathe. The electron is not a marble. It is not a bead. It is something more fluid, more diffuse, more mysterious. And yet, somehow, it forms the foundation of every moment of your life. You begin to picture the early universe, a place so young and so dense that time itself had barely learned how to flow. In that first fraction of a second, The fields that now fill all of space began to take shape. The electron field settled into existence the way a newborn planet cools from molten rock into a quietly spinning sphere. The universe did not assemble electrons out of smaller parts. Instead, the universe cooled into a state where the electron field simply existed, the way a melody can exist once a musician touches a string. From this field, the first electrons emerged, identical to all the electrons that would follow, identical to the ones drifting inside your body right now. Physicists sometimes call this universality, the idea that every electron in the cosmos is exactly the same. That sameness is not an accident. It is a direct consequence of being a fundamental particle. If electrons were made of smaller components, if they were stitched together from tiny pieces the way protons are, then there might be variations. Slight blemishes. Differences in shape or size or structure, but there are none. Every electron is a perfect reflection of every other electron, as though they are all expressions of a single underlying idea rather than individual objects. This is what the experiments at SLIC, CERN, and so many other laboratories have shown again and again. When electrons scatter off one another, or off protons, their behavior reveals no internal complexity. When they dance through magnetic fields in a penning trap, their motion reveals no hidden gears or moving parts. When they interact with photons, the signature of that interaction shows no deviation from what a point-like particle should produce. Even the way electrons tunnel through barriers, slipping through walls of energy as though space momentarily allows them passage, contains no hint of an internal structure slowing them down or altering their probability. You breathe a little deeper, imagining the electron as a quiet visitor. It has no inside to explore, no surface to touch, no hidden compartments to unfold. And yet, it expresses properties that seem rich and layered. It has mass, which arises from its relationship with the Higgs field. It has a charge, which reflects how it interacts with the electromagnetic field. It has spin, which is as intrinsic to it as its very existence. It has a magnetic moment, shaped not only by its own nature but also by the restless fluctuations in the vacuum around it. This vacuum is a strange place. It is not empty space in the ordinary sense. It is a seething ocean of temporary particles that flicker into and out of existence, nudging the electron in subtle ways. These flickers shift the electron's energy ever so slightly, a phenomenon known as vacuum polarization. They change the value of its magnetic moment, creating what physicists call the anomalous G factor. This G factor is one of the most precisely measured quantities in all of physics, and the fact that theory and experiment match so closely is a quiet triumph of our understanding of the electron's nature. You imagine this vacuum now, not as a dark emptiness, but as a faint shimmer beneath reality. It is a field of possibilities, always in motion even when everything appears still. The electron lives in constant dialogue with this vacuum. It is not shaped from smaller pieces. Instead, it is shaped from interactions with the fields that define the universe, interactions with space-time itself, interactions with the ever-changing sea of virtual particles. In this sense, you might think of the electron not as a structure, but as a behavior. It is not something that has an identity because of what lies inside it, but because of the way the universe behaves when an electron is present. When the electron field vibrates, that vibration carries the electron's properties. When the vibration stops, the electron is gone. There is no shell left behind. no husk, no residue. What remains is simply the field, quiet once more. You let your mind drift around that idea, feeling how different it is from the world of everyday objects. If you take apart a chair, you find wood. If you take apart wood, you find cells. Inside cells, you find molecules, and inside those molecules, atoms. Inside atoms, you find nuclei and electrons. Inside the nuclei, you find quarks. But inside the electron, there's nothing to find. You have reached the bottom of the ladder. You have reached one of the universe's indivisible notes. Yet, even though the electron has no interior, it is not without depth. The depth comes from the way it participates in the symphony of forces that hold reality together. The depth comes from the fact that it has persisted for billions of years, unchanged, stable, carrying its properties from the early universe to this moment, inside the atoms of your bloodstream, your bones, your heartbeat. You picture one of these electrons now, not as a dot, but as a cloud of possibility, a probability wave spread out over a region of space. In an atom, the electron is not orbiting the nucleus the way a planet orbits a star. Instead, it forms standing waves, distributions of probability that ripple quietly around the nucleus. The shapes of these waves determine the geometry of molecules, which determines the structure of everything from water to DNA to the cells in your fingertips. It is remarkable that something with no size can still give shape to the world. As you drift deeper into this thought, you begin to sense the quiet unity beneath it all. The electron does not need an inside to matter. It does not need smaller components to be real. It is real because the universe behaves in a way that makes it real. It is real because the electron field exists. It is real because the properties we measure arise reliably, consistently, beautifully from the laws that govern the quantum world. You picture these laws as a gentle framework beneath the universe, invisible yet ever present. They guide the electron, shape its interactions, and give rise to the richness of matter. They ensure that every electron is identical, that every atom is stable, that chemistry has structure, that life can form. The electron is not a container of parts, but a node in this deeper web of laws, a quiet pattern in the fabric of existence. And somewhere in that realization, another question begins to form. Slowly, softly, like a ripple spreading across a calm lake, inviting you to follow it further into the quiet mystery of what lies beyond. And as you drift toward that quiet ripple of curiosity, the world around you seems to fall into a slower rhythm, as though everything is gently waiting for the next layer of understanding to reveal itself. You linger in this stillness for a moment, letting the silence deepen, letting your attention soften until the boundary between thought and space becomes faint and hazy. The next question unfolds in your mind. If an electron has no size, if it is a point-like excitation of a field, then how does it move through space? What does motion even mean when the object you are imagining has no surface? You let that question hang there, like a star suspended in the dark, inviting you closer. In classical physics, objects have positions. A pebble has a location on the ground, a star has a location in the sky, and a planet has a well-defined path as it orbits the sun. But in the quantum world, the electron does not travel on a single, sharp trajectory. Instead, the electron spreads out as a wave of probability. It is more accurate to say it explores all possible routes simultaneously. Richard Feynman's path integral formulation of quantum mechanics revealed this strange truth. To predict where the electron might go, you must consider every path it could possibly take, and then add all those possibilities together, allowing them to interfere like ripples on water. This does not mean the electron smears across space the way a cloud drifts across the sky. It means its existence is described by a wave that encodes possibilities, and the outcome we see is shaped by how those possibilities interact. When an electron is not being measured, the wave spreads, exploring. When it is measured, the wave collapses, revealing a single result. But the spread, the exploration, the quiet exploration of all paths at once, that is part of its nature. A point-like particle with no interior can still participate in an astonishingly rich dance through space. This leads you naturally into another gentle truth, one that physicists discovered through the famous double-slit experiment. If you send electrons one by one toward a screen with two thin openings, tiny specks appear on the far wall. You might expect each electron to choose one slit or the other, leaving simple, predictable marks. But that is not what happens. Even when sent alone, each electron contributes to an interference pattern, a delicate arrangement of bright and dark bands. This pattern only appears when waves overlap. Yet the detector registers electrons, not waves. It is as though the electron passes through both slits at once, interfering with itself, behaving like a wave until the moment it is observed, at which point it behaves like a particle. This experiment has been repeated countless times with electrons, photons, neutrons, even molecules containing dozens of atoms. Each time, the result is the same. The world at small scales is not built from tiny billiard balls. It is woven from probability, interference, and fields. The electron is a point-like excitation, but it behaves like a wave. It carries no internal parts, yet it expresses a profoundly complex set of interactions with the universe around it. You let this paradox settle gently into the quiet space of your mind. The electron is both wave and particle, both point and pattern, both here and everywhere its probability wave reaches. It does not fit neatly into the categories of everyday experience. It is something entirely new, something the human mind was never naturally built to imagine. And yet, through experiment after experiment, we have traced its outlines and glimpsed its nature. You drift deeper into this thought, imagining the electron not as an object, but as a story the universe tells through its fields. The story unfolds differently depending on what the electron encounters. When it meets a magnetic field, it behaves one way. When it encounters a photon, another. When it binds to an atom, it forms ripples that shape the atom's structure. When it flows in a wire, it becomes the current that lights your room. When it absorbs or emits energy, it leaps between states like a stone skipping gently across water. In each case, there is no inside shifting gears or changing shape. There is only the field responding to circumstances, expressing a different mode of vibration. It is like listening to a single violin string. The string has no internal moving parts, but the way it vibrates can create 1,000 different tones. The richness comes not from what is inside the string, but from the laws that govern its motion. In the same way, the richness of the electron arises from the laws of physics themselves, from the properties built into the electron field, the electromagnetic field, and the geometry of space-time. As you drift along this thought, you begin to feel the quiet wonder behind it. The electron is not made of smaller particles, yet it shapes the universe with extraordinary power. It is not composed of parts, yet it gives rise to the structure of atoms, the behavior of chemistry, and the electrical currents that run through your life. It is a simple, indivisible note, and yet it participates in a cosmic symphony so vast that even a lifetime of study would not exhaust its mysteries. You pause for a moment, letting the quiet settle around you. The world slows. Your thoughts soften. The electron, this tiny fundamental entity, becomes a symbol of something larger, a reminder that the foundations of reality are often simpler and more profound than they appear. The electron is what it is not because of what lies inside it, but because the universe itself vibrates in patterns that give rise to such particles. And as you drift toward that distant glow, the question becomes clearer, as though it has been waiting patiently beneath the surface of your awareness. If the electron is a ripple in a field, if it is a vibration with no interior, then what gives rise to the field itself? Where does that quiet, ever-present fabric come from? You rest inside that question, letting it expand. Not in a rushed, analytical way, but softly, like a breath unfolding in the dark. Modern physics suggests that the fields underlying the universe did not emerge gradually. They came into being almost instantly, in the earliest fraction of a second after the Big Bang, during a phase known as symmetry breaking. Before this moment, the universe was unimaginably hot, dense, and uniform. The forces we know today, gravity, electromagnetism, the strong force, the weak force, were woven together in a single, indistinguishable fabric. There were no electrons, no quarks, no atoms. There were only fields, all merging into one. But as the universe expanded and cooled, the symmetries of that early state began to fracture. One by one, the forces separated. The electromagnetic field took on its own identity, distinct from the weak, nuclear field. And with this separation came a new kind of vibration, the one we now call the electron field. Just as a cooled lake forms ripples differently than a boiling one, the cooled universe allowed new modes of vibration, new types of excitations. Electrons were among the first of these excitations, arising as natural expressions of the universe's newly broken symmetry. You imagine this moment not as an explosion, but as a quiet unfolding, like light beginning to soften the edge of a horizon. The universe cooled, the symmetries broke, and suddenly there were particles, not built, not assembled, not stitched together, born. This is why electrons are identical across the cosmos. They do not vary because they do not come from different places or processes. They are all manifestations of the same underlying field, the same fundamental structure of reality. 1 billion electrons in your body carry the same charge, the same mass, the same spin as electrons drifting through distant stars, as electrons born in particle collisions at CERN, as electrons released in a lightning strike miles from where you rest. You let this universality settle into your mind. Every electron you have ever interacted with, through the touch of your hand against a warm surface, through the spark of static electricity, through the flow of current in a wire, has the same identity as the electrons that shaped the earliest stars. The entire universe shares this quiet consistency, as though every electron is a single repeated note from the same cosmic instrument. And yet, even with this astonishing sameness, electrons behave differently depending on their surroundings. Inside an atom, they form standing waves, quiet patterns of probability shaped by the nucleus at the center. These patterns are not circular orbits, but clouds of possibility, spheres, dumbbells, rings, structures determined by solutions to the Schrödinger equation. Each shape defines a different energy level, and when an electron moves between these levels, it absorbs or emits photons in specific colors of light. The glow of a neon sign, the red of a distant star, the soft green of the aurora. All of these are born from electrons stepping between patterns. You imagine these patterns now, not as rigid shapes but as gentle resonances, like the tones that fill a quiet room when a musician lightly touches a string. The shapes of these resonances determine everything: the angles between bonds in a molecule, the strength of an attraction, the color of an emitted photon. Water flows the way it does because electrons arrange themselves in a bent geometry around oxygen atoms. DNA spirals because electrons favor certain bonding patterns and reject others. Even the folding of proteins, those complex, life-defining structures, is shaped by the subtle preferences of electrons as they settle into states of lowest energy. It is astonishing that something with no size, something that is not made of anything, can influence form and function so deeply. Yet this is the quiet power of the electron. It participates in bonds, shapes molecules, defines geometry, and gives rise to the chemical behavior that underlies life itself. As you drift deeper into this realization, you begin to sense a gentle continuity between the smallest scales and the largest. Electrons are present not only in atoms, but in stars. In every beam of light, there is an electron being nudged, excited, accelerated. In every technological device, electrons flow in ordered currents, responding to electric fields with a grace that belies their profound simplicity. You picture a beam of electrons moving through a particle accelerator, guided by magnetic fields into tight spirals. Detectors watch them scatter, curve, emit faint flashes. Each flash reveals something about their nature, and across decades of experiments, from bubble chambers to silicon trackers, from early cathode beams to the most advanced colliders, electrons have behaved with unwavering consistency. No hint of internal structure appears, no evidence of subcomponents, no sign that they are anything but fundamental. This constancy leads you into another quiet question. If electrons have no inside, and if their behavior arises entirely from the fields that define them, then what does it mean for you to be made of matter? What does it mean that everything you know, everything you experience, is constructed from something so ephemeral, so delicate, so unlike the solid surfaces you feel? You rest in this question, not trying to answer it, simply letting it unfold. Matter is not truly solid. Matter is patterns of energy. Matter is fields interacting. Matter is the balance of attractions and repulsions, of resonances settling into shapes. And the electron, with its quiet vibration and its perfect simplicity, is one of the primary artists in this cosmic architecture. It sculpts the world not by having parts, but by influencing the space around it. When electrons move, they create magnetic fields. When they gather, they repel with a force that defines the boundaries of the world you navigate. When they bind to nuclei, they create the structures you recognize as atoms. You drift with that thought, feeling the subtle shift from understanding to wonder. The electron is not a thing you can cut open or analyze from the inside. It is a phenomenon, an expression, a whisper from the universe's earliest moments. It has no interior, yet it shapes everything you have ever known. You let that rising question expand, as though it were opening a gentle doorway into another layer of reality. The curiosity is quiet but steady. If electrons are point-like, if they have no internal parts, if they are nothing more than vibrations in a field, then why do they interact with the world in ways that feel so unmistakably physical? The question settles over you like a soft blanket. A moment passes before the answer begins to unfold. Every interaction an electron participates in comes not from what lies inside it, but from how it couples to other fields. This coupling is a kind of communication, a rule written into the structure of the universe. The electron interacts with the electromagnetic field because its vibration carries a specific kind of charge. That charge is not stored anywhere inside the electron. It is an intrinsic property of the vibration itself, the same way a note played on a violin has a frequency that comes from the vibration, not from hidden mechanisms within the string. Electromagnetism responds to the electron's charge by shaping the space around it. A tiny zone of influence forms, a kind of field pattern that extends infinitely outward, weakening with distance but never fully disappearing. This pattern is what allows electrons to bind to nuclei, to repel other electrons, to create the invisible webs of force that define the shape of matter. The brilliance of this becomes clearer when you think of the hydrogen atom, the simplest atom in the universe. A single electron binds to a single proton. No gears, no shells, no internal structures are needed. The electron's wave function curls around the proton in a stable pattern, held by the electromagnetic attraction. The radius of this pattern, known as the Bohr radius, sets the scale of atoms throughout the cosmos. Every atom in your body follows the same rule, the same quiet geometry. Thought deepens as you picture the electron's wave curling around a nucleus, not as a sphere, but as a hum of a probability. Quantum mechanics does not allow the electron to sit still in one location. Its presence is smeared through space, forming a gentle cloud whose shape depends on the energy of the system. This cloud is not a physical mist. It is a representation of where the electron could be found if measured. Until that moment, the electron occupies all of those possibilities at once. This idea feels abstract until you recall another landmark experiment, one performed in the early 20th century and refined many times since. The Stern-Gerlach experiment revealed that electrons possess spin, an intrinsic twist of their vibration. When sent through a magnetic field, electrons split into two distinct paths rather than a continuous spread. This result puzzled the first physicists who observed it. A spinning object should be able to orient in any direction, yet electrons could only align up or down. Two choices, no in between. Such a restricted, binary behavior could only come from a fundamental property. It is not evidence of structure inside the electron, but evidence of a deep, quantized rule governing its existence. Spin is as fundamental as charge, as mass, as the vibration itself. It shapes everything electrons do. Without spin, atoms would collapse, chemistry would not work, and the rich tapestry of molecules that defines life would never form. You drift through these realizations slowly, letting them settle with a sense of steady wonder. Electrons do not need to contain parts to hold such properties. They express these properties because they are the universe's way of allowing complexity to emerge from simplicity. Another image arises, the electron inside a solid piece of metal. In that environment, electrons are not bound to individual atoms. They flow freely, forming what physicists call a conduction band. The freedom of electrons in such bands is what gives metals their shine, their conductivity, their ability to move energy and charge with such ease. A gentle shift in the arrangement of atoms alters how electrons drift, creating semiconductors, insulators, superconductors, entire families of materials defined not by the inside of electrons, but by the space in which they move. When cooled to extremely low temperatures, some materials allow electrons to pair up in a delicate dance known as Cooper pairing. These pairs move without resistance, giving rise to superconductivity. No internal particle structure is needed for this phenomenon. It arises from the way electrons interact with the lattice of atoms and with one another. The electron remains itself, structureless, point-like, fundamental. Yet the behaviors that emerge from its interactions are breathtakingly complex. Imagine a superconductor cooled to near absolute zero. A ring of metal can carry an electrical current that never fades, a current made of countless electrons moving without friction. This is the quiet power of fundamental particles. They have no interior, but their collective behavior can become something that seems almost alive. Another layer opens as you drift through this thought: the electron's mass. Why does it have mass at all if it contains nothing to weigh it down? The answer leads into the Higgs field, a pervasive energy field that fills all of space. Particles gain mass through their interaction with this field. The electron's vibration couples to the Higgs field at a certain strength, giving it a small but crucial mass. This mass allows electrons to orbit nuclei rather than fly away at the speed of light. If the coupling were slightly different, chemistry would not exist. If it were drastically different, stars could not form. Contemplation deepens as the thought becomes clearer. The electron's mass is not something hidden inside the particle. It is a relationship, a conversation between the electron and the Higgs field. The universe gives the electron its mass the way wind gives shape to a sail. Without the wind, the sail hangs limp. Without the Higgs field, the electron would be weightless, racing through space too quickly to form atoms. As your mind drifts along this idea, a sense of calm resonance emerges. Electrons teach you that reality is built not from small objects, but from interactions, from relationships, from fields whispering to one another through the fabric of space-time. This is why the electron does not need an interior. Its entire identity arises from the rules that define its existence and the fields that surround it. Another question glides quietly into view, not abrupt, not rushed, but soft and inviting. If the electron is so simple, so fundamental, then why does the world built from it feel so rich, so textured, so endlessly complex? You let that distant star of a question draw you closer, not with urgency, but with the natural pull of curiosity, the kind that guides you gently deeper into the heart of things. The world built from electrons feels rich, textured, layered with light and shadow. This richness seems hard to reconcile with the idea of a particle that has no interior, no size, no complexity. Yet the very contrast holds the key to understanding the universe on its smallest scales. The richness of the world does not come from the complexity of the building blocks themselves. It comes from the complexity of how they interact. A grain of sand can form a dune. A drop of water can carve a canyon. Simple pieces, shaped by laws that play out over time, can create forms that appear intricate and alive. In the same way, the electron's simplicity allows it to participate effortlessly in vast networks of interactions. Because all electrons are identical, the universe can rely on them as consistent collaborators, weaving stability out of the quiet hum of repeated behavior. Picture an electron in a copper wire. It is driven forward by an electric field, drifting slowly while passing energy from atom to atom. The motion of each individual electron is subtle and erratic, guided by quantum fluctuations. Yet, when billions of electrons move together, they form a steady electrical current. That current powers lights, feeds cities, runs through the device you are holding. A single electron has no complexity inside it. The collective life of electrons, however, creates entire worlds of function and possibility. The richness becomes even clearer when you step into the microscopic realm of chemistry. Electrons define the behavior of atoms, not through their internal parts, but through the shapes of their wave functions. These shapes create bonds, some strong, some weak, some flexible, some rigid. They allow carbon to form long chains, rings, lattices. They allow oxygen to cling to hydrogen in a way that bends light and shapes oceans. They allow iron to gather into the core of a planet, and gold to settle in veins deep underground. The variety of chemical behavior springs from the geometry of electron waves, not from anything hidden inside electrons themselves. This idea grows even more astonishing when you consider that electrons also shape the colors you see. When an electron shifts between energy levels in an atom, it can emit or absorb light of a specific color. The blue of a gas flame, the green of emeralds, the deep red of a sunset. Each arises from electrons moving between quantized states. These transitions are not driven by internal complexity. They are driven by rules of energy, symmetry, and probability, all connected to the electron's relationship with the electromagnetic field. Thought deepens as you drift into the realm of quantum electrodynamics, often called the most accurate physical theory ever devised. QED describes how electrons interact with photons, how fields ripple and respond. It has predicted numbers, like the electron's magnetic moment, with precision so extraordinary that experiments have confirmed them to countless decimal places. The accuracy is not the result of electrons having intricate internal workings. Its success comes from the purity of the electron as a fundamental particle, one whose simplicity makes its behavior mathematically precise. Richard Feynman once remarked that QED might be the jewel of physics, a theory so accurate that if theory and experiment disagreed by even the tiniest margin, some new physics would almost certainly be waiting to be discovered. Yet the agreement has held firm. Every electron measured behaves exactly as the theory predicts. No deviations, no anomalies, no hints of a deeper substructure. This remarkable consistency strengthens the idea that electrons are truly elementary, irreducible pieces of reality. If electrons are truly fundamental, if they have no interior and no layers to peel back, then does that mean we have reached the ultimate bottom of the universe? Or could there still be something deeper hiding beneath the fields themselves? Physicists have explored this question for decades. Some theories propose that particles might be excitations of even more fundamental strings, tiny filaments vibrating in multiple dimensions. In such theories, the electron's properties arise from the way a string vibrates. Yet these ideas remain untested, distant, intriguing, but not confirmed. There is no experimental evidence that electrons have any additional structure. High-energy scattering experiments have pushed the limits as far as current technology allows, and each time the electron appears point-like, featureless, perfectly smooth. Quantum fields remain the most successful description we have. They are not simply mathematical constructs, they have measurable consequences. Field theories predict particle interactions, decay rates, scattering angles, energy distributions. Every successful prediction reinforces the idea that fields are real in a physical sense, perhaps as real as space and time themselves. When an electron appears in a detector, it is the field announcing that it has vibrated in a particular way. You begin to imagine these fields now, not as abstract equations, but as quiet, invisible oceans stretching across the universe. Each field permeates every point in space. The electron field waits everywhere, even in the space around you. Most of the time, it lies in a calm ground state. Only when excited does it ripple, and the ripple we observe is what we call an electron. There is no inside to explore. The ripple is the phenomenon. This leads to a kind of quiet, philosophical reflection. The solidity you experience, the world you interact with, the sensations that guide you through your daily life, all of them arise from interactions between fields, not from the bulk or thickness of physical material. You are not made from tiny, solid spheres stacked together. You are made from patterns in a vast, silent tapestry. Mass arises from interactions. Charge arises from interactions. Bonding arises from interactions. Even the idea of presence arises from how fields respond to one another. The electron, with no interior structure, shows you that the universe does not require complexity in its building blocks. The complexity emerges from the rules, not from the ingredients. Another layer of the story appears as you drift toward it. Electrons, along with quarks and neutrinos, belong to a family of particles called fermions. Fermions obey the Pauli exclusion principle, which states that no two identical fermions can occupy the same quantum state. This simple rule shapes the universe in ways that are almost impossible to overstate. It is the reason atoms have shells. It is the reason matter takes up space. It is the reason white dwarf stars resist collapse. Without this rule, electrons would pile into the lowest energy states, and atoms would crumple into featureless nuggets of collapsed matter. The Pauli exclusion principle is not a result of hidden parts inside electrons. It is a fundamental property of fermions, baked into the mathematics of quantum mechanics. Electrons obey it because of their nature, not because of their structure. They produce the world you know because the universe has gifted them with this quiet rule about sharing space. You linger with that realization, letting it shape your understanding of matter. The world feels solid under your hand because electrons refuse to share identical states. The stability of your body, the air around you, the ground beneath you, all of it emerges from the behavior of electrons that have no interior. They create vast complexity through simple, universal principles. Thought expands further as you drift into the cosmic scale. Stars shine because electrons and atoms jump between energy states, releasing photons. Planetary atmospheres form because molecules shaped by electron bonds cling to worlds. The glow of a distant galaxy arrives in your eyes because electrons within the detectors on telescopes register the incoming light. Electrons participate in the birth of stars, the life of planets, the chemistry of oceans, the function of cells, the firing of neurons. This tiny, structureless particle touches everything. If electrons shape the universe so profoundly, then what role do they play in the very act of perception, in the way your mind experiences reality itself? A faint pulse of curiosity gathers at the edges of awareness, rising like a soft current beneath still water. The question hovering there feels larger than the particle that inspired it. What role does the electron play in perception itself, in the intimate act of experiencing the world? Perception begins long before thought. It starts with the simple meeting of light and matter. Every time a photon touches the retina of an eye, it interacts with an electron in a molecule called rhodopsin. The electron absorbs the photon's energy, shifts to a new configuration, and triggers a chemical cascade. That cascade becomes an electrical signal. The signal becomes a pattern in the brain. The pattern becomes a moment of sight. This delicate dance happens countless times per second. Light arrives. Electrons respond. Images appear. None of this requires electrons to have structure. Their ability to absorb and release energy comes from their quantized nature, from the specific ways they can shift between allowed states. The world you see, in all its depth and color, is shaped not by the content inside electrons, but by the strict rules that govern their transitions. Thought sharpens as another layer comes into view. Perception is not only about sight. Touch, too, arises from electrons interacting with electrons. When a fingertip brushes a surface, the sensation does not come from atoms physically colliding. It comes from the repulsion between electron clouds. The sense of pressure is the brain interpreting these repulsive forces. Even warmth is the result of electrons in atoms vibrating more vigorously and transferring that motion through collisions and fields. Taste and smell rely on shapes, molecules fitting into receptors like keys in locks. Those shapes are defined by electron configurations, by the geometry that arises from the balance of repulsion and attraction inside molecules. Sound is carried by vibrating air molecules, whose behavior depends on electron bonds that give gases their properties. In every sense, electrons give texture to experience. They provide the rules that allow perception to exist. The idea settles that the richness of your inner world is built upon the simplicity of a particle with no interior. Complexity emerges without complexity in the components. That realization feels almost paradoxical, yet it is one of the universe's most elegant truths. Thought drifts now into the brain itself, a structure built from cells whose activity depends on the controlled movement of electrons and ions. Nerve impulses travel along neurons because channels open, allowing charged particles to flow. These flows create voltage changes. Those changes propagate like waves along the neural pathways, forming circuits of thought, memory, emotion, identity. Each spark, each firing pattern, each quiet moment when a memory resurfaces is tied to electrons in motion, electrons transferring charge, electrons responding to fields. The sense of self, with all its depth and subtlety, rests partly on the behavior of electrons that never change, that never vary, that never reveal even the hint of internal detail. The same type of particle that shaped the earliest stars now shapes the currents that define consciousness. A new question forms slowly, rising like a gentle tide. How can something so small, so uniform, be so deeply involved in phenomena as vast as galaxies and as intimate as thought? The answer begins by considering scale. Electrons help shape stars because their interactions determine how atoms form and how energy flows. In the hearts of stars, electrons help mediate fusion reactions. When hydrogen nuclei press close enough together, electrons create the conditions that allow them to merge, releasing the energy that warms planets and seeds galaxies with heavier elements. On the other hand, electrons shape consciousness because they give structure to molecules and enable the precise electrical behavior of neurons. The same rules that guide an electron in a distant nebula guide an electron in a synapse of the human brain. Uniformity allows universality. Universality allows elegance. That elegance permeates everything, from the birth of stars to the quiet emergence of introspection. A sense of quiet continuity emerges. The same electron that ripples in distant galaxies ripples within organisms, linking the smallest patterns of the cosmos to the smallest patterns of thought. The universe does not separate the cosmic from the personal. It uses the same tools in both places. Another layer unfolds. Many physicists believe that electrons, through their wave-like nature, remind us that reality is not built from individual objects, but from patterns. A single electron in an atom occupies a wave function spread across space. The identity of the electron is not a point, but a distribution of possibility. This wave function interferes with itself, binds with others, organizes into shells that give atoms their structure. These shells determine which chemicals can exist, which reactions can occur, which forms life may take. Life is built on the architecture of probability. Each cell, each molecule, each organ arises from rules that originate in the simplest of quantum behaviors. Nothing inside the electron needs to be complex. The complexity arises from the choreography of electrons in groups, from the collective interplay of their wave functions. The unity of these ideas begins to feel almost meditative. A vast universe emerges from a handful of fundamental particles that have no hidden parts. The electrons in your body are indistinguishable from electrons that formed in the early universe billions of years ago. They have traveled through stars, through interstellar dust, through countless interactions, and now inhabit the delicate architecture of your cells. Their properties have not changed. They have no memory of their journey. Yet they help shape your memories every moment of your life. Reflection deepens. Perhaps the electron shows that complexity does not need to reside in the smallest pieces. It can arise from the relationships between them, from the rhythms they follow, from the rules that govern their behavior. It suggests that identity in the universe is not defined by what lies inside, but by how things interact. A calm thought settles in. The nature of the electron is a reminder that understanding oneself is not about dissecting the pieces, but about recognizing the patterns, the connections, the story that emerges from the whole. Just as electrons reveal their meaning through interaction, humans reveal their meaning through connection, through the quiet spaces between experiences, through the reflections that guide them forward. What might lie beyond electrons and fields, beyond the descriptions we have crafted, beyond the boundaries of current understanding, hidden in the deeper layers of quantum reality? A gentle pause gathers around the question, as though the cosmos itself is inhaling before offering the next layer. The edges of thought soften, and the ideas you have been drifting through begin to settle like dust in a sunbeam. The mystery of electrons feels clearer now, yet the wonder remains untouched. From that stillness, the next question does not rise abruptly. It arrives slowly, blending into the moment with the natural ease of a tide returning to shore. The inquiry begins to expand in a quiet, seamless way. If the electron is fundamental, if it has no interior and no smaller building blocks, then what lies beneath the fields that define it? What waits in the deeper structure of quantum reality, beneath even the clean simplicity of the standard model. This transition feels less like turning a page and more like gently sinking into a deeper layer of the same story. The electron, after all, is not an isolated mystery. It is a doorway, a hint that the universe may have foundations more subtle than particles and waves alone. Thought drifts toward the fields themselves. Quantum fields are not objects. They are not made of anything either. They are, as far as we understand, the primary scaffolding of reality, the invisible medium from which particles arise. The electron field, the photon field, the Higgs field. Each permeates all of space, silent until stirred. A sense of continuity unfolds. The simplicity of the electron becomes a clue that the universe may be rooted in principles rather than pieces. If fields give rise to particles, then the next natural question becomes, what gives rise to fields? This line of thinking has guided physicists for decades. Some suspect that the fields are themselves emergent, that they are patterns arising from something deeper, the way waves on water arise from countless molecules moving in concert. Others wonder if the fields might be manifestations of geometry, perhaps tied to the shape of space-time in dimensions beyond the familiar three. There are theories that speak of strings and brains, theories that imagine space-time itself quantized, theories that treat information as the most fundamental substance of all. None of these ideas have been confirmed, yet each one carries a quiet resonance, a sense that the electron's point-like nature is not an end, but an invitation. The perfect smoothness of the electron hints that whatever lies deeper must be subtle, elusive, and delicately woven into the structure of reality. Consider the notion of quantum foam, a concept proposed by John Wheeler. At unimaginably tiny scales, far smaller than atoms, far smaller than protons, space-time may fluctuate wildly, bubbling and twisting in ways that defy classical logic. In such a realm, ideas like distance and direction might lose meaning. The smooth fields we observe could be averages of something far more chaotic and primal. In this picture, electrons might be stable patterns formed within that foam, persistent notes arising from the restless fluctuations of the quantum vacuum. Another idea emerges from supersymmetry, the elegant notion that every particle has a partner. If supersymmetry exists, electrons would have counterparts with different spins and different behaviors. These partners, if found, could reshape our understanding of the electron's place in the universe. They would help unify forces and clarify the inner workings of the quantum fields. But so far, no supersymmetric particles have been observed. The theories remain whispers, possibilities waiting for evidence. String theory offers a different vision. In that framework, electrons are not points at all. They are tiny, vibrating strings whose modes of vibration determine mass, charge, and spin. The electron's apparent lack of structure would not be a mystery. It would simply be a reflection of the string's size being far beyond the reach of current experiments. If strings are real, their scale would be so small that even the most powerful colliders humans have built would not be able to resolve them. The electron would appear point-like, not because it is truly without extent, but because its true nature lies far beyond the resolution of our tools. These possibilities do not contradict the electron's behavior. They simply offer different interpretations of the deeper layers beneath that behavior. The experiments we perform reveal the electron's properties, but they cannot yet reveal what gives rise to those properties. In this sense, the electron becomes a lantern, illuminating the path ahead while keeping the deeper terrain hidden in soft shadow. It is this blend of clarity and mystery that makes the electron such a powerful guide into the nature of reality. The particle shows us that the universe is not made of little spheres. It is made of relationships, rules, symmetries, and vibrations. The question of what lies beneath is not a transition to a new topic, but a natural deepening, as though diving from the surface of a lake into its calm, dark water. Thought settles into this continuity, feeling how the inquiry threads itself seamlessly through each idea. Beneath particles lie fields. Beneath fields may lie something even more fundamental, perhaps a new kind of geometry, perhaps an underlying informational structure, perhaps something the human mind has not yet conceived. As this understanding takes shape, a sense of gentle anticipation forms, not the restless kind that urges speed, but the quiet kind that invites depth. The universe feels like a story that is still unfolding, each layer revealing another, each question easing into the next without ever truly breaking the flow. Another question begins to shimmer at the edge of awareness, subtle, patient, carrying you further along the same gentle descent. What happens when we follow the electron all the way down to the limits of measurement, to the boundary where space itself begins to blur? The limit of measurement arrives not with a dramatic boundary, but with a quiet narrowing. As energies rise and distances shrink, experiments begin to lose the ability to distinguish one point from another. The resolution of a particle accelerator works like the zoom of a microscope. The higher the energy, the finer the details it can probe. For decades, physicists have pushed this zoom as far as technology will allow, hurling electrons toward targets with increasingly immense energy. At some point, even the most powerful collisions reveal nothing new. The scattering pattern remains clean, structureless, consistent. No signs of internal layers, no ripples that suggest an underlying texture. The electron behaves as a perfect point, responding to forces exactly the way a fundamental particle should. This consistency is not the silence of ignorance. It is the silence of precision. Every experiment, the ones using crystal detectors, gas chambers, silicon trackers, magnetic spectrometers, confirms the same story. The electron remains unbroken. Approaching the limits of measurement is like approaching the edge of a fog. You can see farther with better instruments, but eventually the landscape ahead becomes indistinguishable. The electron dissolves not into new components, but into the boundaries of space-time itself. Beyond a certain scale, the meaning of position begins to unravel. The uncertainty principle asserts itself with quiet authority, narrowing the location of the electron force's enormous uncertainty in its momentum. Attempts to force a sharper picture only flood the scene with more energy, more noise, more distortion. Space-time at these scales is no longer a smooth backdrop. It becomes a restless medium, fluctuating, jittering, refusing to remain still. The electron moves through this realm not as an object traveling through a landscape, but as a pattern woven into the fabric. The closer the measurement, the more the measurement itself becomes part of the story. A probe energetic enough to resolve smaller distances would distort space-time so violently that the region would collapse into confusion. Some theories suggest even into microscopic black holes. Even if that extreme never occurs, the idea illustrates something deeper. The universe does not offer limitless clarity. It offers laws, and those laws place boundaries on what can be known. Reaching this boundary does not diminish the electron's meaning. it heightens it. The electron's point-like nature is not a temporary placeholder awaiting discovery of smaller parts. It is a reflection of how reality expresses itself at the most fundamental level available to us. The field that gives rise to the electron is continuous, ever present, and the particle is the smallest stable vibration it can support. Asking for an interior becomes as misplaced as asking for an interior to a frequency. A wave is defined by its behavior, not by what it contains. Moving through this understanding feels like descending through layers of conceptual noise, stripping away assumptions until only the essentials remain. Mass arises from the Higgs field. Charge arises from the electron's coupling to the electromagnetic field. Stability arises from its adherence to the exclusion principle. Motion arises from the undulation of its wave function. Every one of these properties is outward-facing. None emerges from a hidden interior. Within this realization, the boundaries of particle physics begin to connect with the boundaries of space-time itself. When probing scales so small that position loses meaning, the quest turns from asking what an electron is made of to asking how the universe holds the electron in place at all. The point-like nature is not a deficiency in understanding. It is the final shape of understanding at this layer of reality. The electron is not a container, but a behavior. It is not a structure, but a mode of existence. The deepening perspective makes the world feel both simpler and more intricate. Simpler because the electron is elemental. Intricate because everything built from electrons takes on such elaborate form. Chemical bonds, molecular geometries, crystalline lattices, biological networks. They all arise from the interactions of something that has no dimension. The complexity emerges entirely from relationships. Following the electron into these limits brings a kind of quiet revelation. At the smallest scales, the universe does not offer a hidden machine or clockwork interior. It offers patterns, interactions, rules, symmetries that break, then give rise to new forms. Space-time that supports fields, and fields that support particles. The electron is a stable note in this cosmic symphony. Its perfection is not emptiness, it is elegance. As the understanding settles, the descent continues naturally, not by leaping into another question, but by allowing the implications to unfold. At the boundary where space-time begins to blur, where measurement loses its meaning, the electron stands not as a puzzle but as a guide, pointing toward the deeper architecture of reality that shapes everything from the birth of stars to the quiet rhythms of thought. The structure of reality grows stranger the further the electron guides you. Once you move past the limits of measurement, past the smooth surfaces of theory, a different kind of understanding begins to take shape. One that does not rely on peeling open the particle, but on watching how the universe arranges itself around it. The standard model places the electron among a set of fundamental particles with no known substructure. Nothing inside, nothing beneath. Yet the model itself is not a closed book. It is complete enough to describe the known interactions, but incomplete in the way a beautiful machine might run flawlessly, while still revealing hints that its origin lies in a deeper design. This deeper design becomes visible in symmetries. Every field in the standard model is tied to a symmetry, and those symmetries dictate what is possible and what is forbidden. The electron's field exists because the universe supports a very specific kind of symmetry, one that governs how it interacts with electromagnetism. Its charge, its coupling, its mathematical behavior all trace back to this quiet rule holding the cosmos together. Symmetry is not an abstract decoration, it is the scaffolding of existence. When symmetry is perfect, particles remain massless. When symmetry breaks, particles acquire mass through interactions with the Higgs field. The electron's mass is small because the symmetry that gives rise to it is broken only gently. There is no hidden mechanism inside the electron doing this work. The universe itself provides the weight, sculpting the particle through its fields. As the path continues, the fields begin to feel less like invisible substances and more like the architecture of reality. Space is not an empty stage on which particles perform. The stage and the actors are intertwined. The electron field fills all of space in the same way the Higgs field does, the same way the electromagnetic field does. These fields overlap, resonate, exchange energy, and stabilize one another. The electron is simply the smallest sustained vibration in one of these ever-present oceans. At this depth, old intuitions fall away. There is no room for mental images of marbles or miniature planets. The electron's identity is not found in a shape or a size, but in the exact pattern the universe supports when its field ripples. Every experiment, from particle traps to high-energy collisions, points to the same truth. When the electron appears, it appears whole. No fragments, no seams, no variation. This continuity guides you past the boundaries of everyday physics into the slow, murmuring domain of renormalization. Renormalization is the mathematical process that allows physicists to make sense of infinities in quantum theories. Instead of revealing that particles hide internal parts, renormalization shows that their apparent properties arise from interactions with the vacuum. The electron's mass and charge are not raw ingredients. They are dressed values, shaped by the constant flurry of virtual particles flickering around them. Even the vacuum contributes. It shapes the electron without ever becoming part of it, the way wind shapes a flame without adding fuel. Nothing inside the electron creates these effects. They arise from the environment in which the electron exists, the sea of fields, the fabric of space-time, the restless quantum vacuum. And as each idea settles, the picture becomes clearer. The deeper the descent, the more the electron dissolves into a relationship rather than a thing. A vibration in a field. A coupling to the Higgs. A charge interacting with electromagnetism. A fermion shaped by exclusion. A participant in quantum vacuum fluctuations. Every property comes from the universe responding to the electron's presence, not from any internal machinery. This leads into another layer without a change in tone or direction. Understanding shifts from looking inward to looking outward. What makes the electron fundamental is not what it contains, but the fact that the laws of nature cannot be written without it. Remove electrons, and chemistry collapses. Remove electrons, and atoms lose their structure. Remove electrons, and stars cannot burn. Molecules cannot form, and the universe becomes a dim and silent place devoid of complexity. The electron is not a building block in the sense of a brick. It is a building block in the sense of a concept, a rule, a fundamental mode of vibration that the universe relies on to express structure. Its simplicity allows everything else to become intricate. The absence of layers inside it becomes the foundation for layers everywhere else. The path continues downward, yet nothing has to be forced or punctuated. One idea flows into the next the way gravity pulls water toward stillness. The electron's identity rests on the elegance of its relationships. Its presence in the cosmic symphony is steady, unbroken, and essential. no endings, no cliffhangers, no abrupt pivots. Just a deepening sense that each layer of understanding is part of the same quiet, seamless descent into the nature of existence. And the descent can continue as long as you'd like, revealing more of the architecture that holds the electron in place, more of the fields and symmetries beneath it, more of the strange and beautiful fabric of reality that allows a dimensionless particle to sculpt the universe. The deeper structure of the electron's world begins to steady itself into something surprisingly elegant. Once the idea of peeling open the particle is abandoned, the attention naturally shifts to the stage on which it exists. Space is not a blank canvas. It carries tension, curvature, hidden energy, and all of these influence how the electron behaves. In quantum electrodynamics, the electron is surrounded by a haze of virtual particles, brief, flickering disturbances that appear and vanish too quickly to be observed directly. This cloud is not an adornment or a decoration. It contributes to the electron's effective charge, its mass, even the way it responds to magnetic fields. The electron is never alone, never isolated. It is always in dialogue with the vacuum. Whenever the electron moves through space, this cloud reforms around it instantly. If you were able to freeze time and look closely, closer than any instrument will ever allow, you would not find a tiny kernel wrapped in layers. You would find a point-like excitation accompanied by an orchestra of momentary interactions. The richness you might assume comes from an interior actually comes from the environment. The vacuum sculpts the particle. The fields sculpt the vacuum. Everything shapes everything else. The notion begins to settle that the electron is not defined by internal complexity, but by the complexity of its context. Space-time does not passively hold the electron. It supports it, shapes it, influences its properties at every scale. Even the fact that the electron does not decay, that it persists for billions of years without changing identity, is a consequence of the deep symmetries that govern the quantum world. Conservation laws hold it in place. Electric charge, lepton number, and the structure of the Standard Model all reinforce its stability. High-energy experiments tell this same story in their own language. When electrons are smashed together or hurled into collisions with other particles, the results are always pristine. Their trajectories bend exactly as expected. Their scattering angles match predictions. Their interactions show no deviation from the behavior of a true fundamental particle. If there were structure hidden beneath the surface, these collisions would reveal tiny shifts, small irregularities, clues that something more complicated was happening beneath the point-like exterior. Yet every experiment has returned the same clean signature. The picture grows clearer. The more violently the electron is tested, the more firmly it displays its simplicity. This simplicity is not emptiness, it is unity. The electron's lack of internal parts is part of its role in the architecture of physical law. It is not a fragment of something larger. It is one of the universe's original notes. Its properties were set in place during the earliest instance after the Big Bang, when the symmetries of the primordial universe cracked and new modes of existence crystallized. The electron's mass, its charge, its spin, all of them sprang from that shift like facets of a gemstone forming as molten material cools. Every electron in the universe is a reflection of that moment. They do not age. They do not weather. They do not drift from one form to another. They remain perfect echoes of the symmetry that produced them. Even now, the electrons in your body carry the exact same characteristics as those formed in the earliest stars. They are timeless participants in the unfolding of matter. Fields, symmetries, the vacuum, the Higgs mechanism. These are the layers that give the electron its identity. None of them reside inside the particle. They reside in the universe itself. The electron is a point where these principles converge, where the rules of reality express themselves in the smallest possible way. Patterns emerge from that simplicity. Atoms form. Molecules take shape. Materials develop their unusual properties. Life begins weaving its own designs. None of these require electrons to contain anything. They only require electrons to behave exactly as they do. Small, stable, identical, guided by elegant laws. The deeper the exploration goes, the more the electron feels like a hinge between the abstract and the tangible. It is small enough to be governed by pure mathematics, yet influential enough to determine the shapes and functions of everything familiar. It lives at the intersection of theory and experience, linking the inaccessible depths of quantum fields with the everyday solidity of matter. The path forward does not need to signal itself or shift tone. The ideas ahead unfold naturally from what has already been revealed, as the nature of the electron opens into the broader story of how the universe builds complexity from simplicity. The electron's simplicity becomes even more striking when it is placed inside extreme environments. In ordinary matter, it shapes chemistry. Inside metals, it forms conduction bands. In biological systems, it carries signals. Yet, when it plunges into the heart of a neutron star, or finds itself in the searing conditions of an early universe plasma, its nature does not shift. The surroundings distort. Pressure grows to unimaginable levels. Magnetic fields twist and roar with violent intensity. But the electron remains unchanged, its identity anchored by the deep symmetries that define it. This stability allows matter to behave predictably, even in places where intuition begins to crack. In the crushing gravity of a neutron star's crust, electrons become so tightly packed that their quantum states fill up to enormous energies. The pressure you find in such a star, an entire sun's worth of mass held inside a sphere the size of a city, comes not from nuclear forces but from the refusal of electrons to share identical quantum states. The exclusion principle pushes back against gravity, creating a kind of cosmic resilience that allows the star to hold its shape. The electron's lack of internal structure is not a weakness in such a place. It is one of the reasons the crust can resist collapse. This kind of stability echoes through many corners of physics. When electrons pair up to form Cooper pairs in superconductors, the phenomenon does not arise because electrons hide complex inner machinery. It happens because the surrounding lattice allows them to interact in a particular way, creating a state where electrical resistance vanishes. The pairing is fragile yet profound, a reminder that emergent behavior can arise from particles that remain fundamentally simple. Even in particle collisions, those brief instants where energies spike to levels found nowhere else in the universe except its birth, the electron remains intact. Accelerators like LEP and the LHC have hurled electrons and their antimatter twins into head-on collisions at staggering energies. Detectors record every fragment that emerges from the impact, mapping the showers of particles that scatter outward. Nothing in those patterns hints at a deeper structure inside the electron. No subparticles emerge. No deviations appear. Every attempt to provoke complexity inside it leads back to the same result: a point-like particle with perfect consistency. This consistency holds even in the presence of the strongest magnetic fields ever observed. Fields around magnetars, where space-time itself seems strained. In such environments, electrons spiral with enormous energy, emitting synchrotron radiation that can be detected across vast distances. Their motion is extreme, but their identity remains the same. They glide along the magnetic field lines exactly as predicted by quantum electrodynamics, leaving behind no sign that anything inside them shifts or ruptures under the strain. The more deeply you look, the more the electron begins to resemble a kind of boundary. On one side, the familiar world unfolds: atoms, molecules, chemistry, life. On the other, the abstract landscape of quantum fields stretches out, with the electron acting as a bridge between the concrete and the conceptual. Its simplicity allows it to sit at this intersection without contradiction. It does not need gears or layers or hidden chambers. Its role is carried entirely by the laws of the fields it inhabits. Those laws are what give the electron weight, charge, stability, and the ability to stitch the universe into coherent structures. Every one of those properties comes from outside the particle. The Higgs field gives mass. The electromagnetic field gives charge interactions. The vacuum contributes fluctuations. Symmetry provides stability. Even the exclusion principle, which prevents electrons from crashing into identical states, arises from the mathematical form of their wave functions, rather than any physical structure inside them. This shift, from searching for content to recognizing relationship, changes the way the electron is understood. It dissolves the idea that fundamental particles should be miniature versions of everyday objects. They are not beads. They are not clusters. They are not shells filled with smaller things. They are expressions of the universe's rules, formed exactly the way a note is formed when a string vibrates. The note is not an object. It is a state, a behavior, a manifestation of the medium. That same logic extends outward into the larger universe. Every element on the periodic table exists because electrons arrange themselves around nuclei in precise ways. Every chemical reaction follows paths dictated by electron energies. The entire palette of matter, hardness, softness, color, conductivity, transparency, emerges from electrons interacting with fields and with one another. The clarity of their simplicity acts like a hinge on which the entire complexity of matter turns. No step in this descent needs setup, foreshadowing, or ritual. Each idea carries the next naturally: particles in fields, fields in space-time, space-time holding everything in place, and the electron moving through all of it with the same unbroken identity it has had since the universe was young. The character of the electron becomes even more striking when viewed through the lens of energy landscapes rather than particles. In quantum mechanics, every allowed state of an electron corresponds to a specific configuration of energy. These configurations do not exist inside the particle. They exist in the space around it. When an electron settles into an atom, it occupies a standing wave shaped by the pull of the nucleus. The architecture of that wave defines the identity of the atom itself. Hydrogen forms one structure, carbon forms another, and the infinite variety of matter arises from these subtle differences in how the electron's presence settles into place. The shapes of these waves determine everything that follows. They dictate how atoms link into chains, how molecules bend or stretch, how proteins fold. They control whether a material conducts electricity or insulates against it, whether it glows when heated or remains dark, whether it becomes magnetic or remains neutral. None of this behavior comes from any internal workings of the electron. Every feature arises from the way the electron interacts with its environment and with the other fields that saturate space. Those interactions lead naturally into the concept of quantization. Energy comes in discrete steps, not because electrons contain gears that lock into position, but because the mathematics of wave patterns allows only certain solutions. These constraints are as fundamental as the rules that govern harmonics on a vibrating string. The electron behaves like a note in a cosmic instrument, with its allowed energies corresponding to the frequencies the universe permits. When it absorbs energy, the pattern swells into a higher form. When it releases energy, the pattern contracts. Light is born from these transitions, carrying away the difference as a photon. The precision of this process reveals the depth of the electron's consistency. Spectral lines, thin fingerprints of light emitted by atoms, match theoretical predictions with extraordinary accuracy. The bright lines in the glow of hydrogen observed in distant galaxies have the same structure as those created in laboratories on Earth. This unwavering match is evidence that the electron's identity has not changed since the earliest stars formed. A particle with internal structure would likely show subtle variations under extreme pressure, temperature, or age. Yet electrons do not drift from one form to another. Their stability is absolute. That stability becomes even more important in the context of nuclear reactions. During fusion in the cores of stars, electrons shape the environment in which nuclei slide together. Their presence defines how atoms assemble and how plasma behaves. As temperatures climb to millions of degrees, electrons break free from nuclei and form a seething ocean around them. Even in these violent conditions, their behavior follows the same mathematical rules, the same couplings, the same interactions. Their nature remains untouched. Beyond the stellar interior, electrons guide the behavior of matter as it condenses into dust, collapses into planets, rises into atmospheres, and cools into the familiar landscapes of chemistry. They define the way atoms attract one another, how gases compress, how liquids flow, how solids crystallize. The entire visible world is shaped by electrons resisting overcrowding and arranging themselves into the lowest energy patterns available. There is no need for internal components to produce this richness. The patterns themselves carry the complexity. At even lower temperatures, electrons reveal a different kind of subtlety. When cooled near absolute zero, some materials allow electrons to move without resistance. This phenomenon, superconductivity, emerges not from the electron changing identity, but from the environment allowing electrons to cooperate. Their wave functions spread and overlap, forming a collective state that moves as a single unified rhythm. The electrons remain fundamental. The new behavior arises from their capacity to synchronize under the right conditions. Extreme cold produces another remarkable effect. In systems known as quantum Hall states, electrons confined to two-dimensional planes under strong magnetic fields begin to display bizarre, quantized behavior. Electrical conductance steps into precise integer values as though following a hidden counting mechanism built into the universe. Once again, none of this reveals internal structure in the electron. Instead, it shows how the electron's fundamental nature interacts with the geometry of space and the presence of fields. This interplay between particle, field, and environment repeats everywhere. It is the reason electrons can form bound states, flow in currents, tunnel through barriers, and generate magnetism. These behaviors do not point inward toward hidden machinery. They point outward to the laws that govern everything. The electron's role is to respond in ways that are perfectly consistent, perfectly predictable, perfectly stable. The deeper the exploration goes, the more the electron resembles a fundamental unit of interaction rather than a tiny object. It acts as a node in a vast network of fields, something that exists because the universe permits a specific kind of vibration, and nothing more complicated than that. The details of matter emerge not from the electron's interior, but from the tapestry of relationships it participates in, the I constraints it follows, and the harmonies it helps form in the structure of space-time. The narrative of the electron settles into a kind of clarity once this perspective takes hold. It never reveals smaller components because none exist. It does not change identity because it is one of the universe's original forms. Its behavior remains consistent across all conditions because the laws governing it are woven into the fabric of reality. Every part of the material world carries traces of these interactions, each moment shaped by the quiet presence of a particle that needs no internal depth to create endless variety. In crystalline structures, electrons settle into patterns that resemble standing waves woven through a rigid lattice. The periodic arrangement of atoms forces the electron's wave functions into bands, distinct layers of allowed energies separated by forbidden gaps. These bands control how the material behaves, whether it bends light, carries current, or remains inert. A conductor has overlapping bands that allow electrons to move freely. An insulator has bands separated by wide gaps that trap electrons in place. A semiconductor sits delicately between the two, with electrons able to cross the gap only when nudged by heat or light. Nothing in these behaviors requires the electron to contain layers of its own. The complexity lies in the structure around it. In magnetic materials, electrons contribute their intrinsic spin. This property, which has no classical analogy, arises from the mathematical nature of the electron's wave function. It behaves as if the electron carries a tiny angular momentum, even though it has no physical size. When many electrons in a material align their spins in the same direction, a macroscopic magnetic field emerges, strong enough to influence metal, guide compasses, or shape plasma in fusion reactors. The underlying mechanism requires no internal parts. The alignment is a collective phenomenon, a pattern of orientation imprinted on millions of identical particles. Inside atoms heavier than hydrogen, electrons fill shells in a rigid sequence. Lower energy states must be occupied before higher ones can be filled. This structure gives the periodic table its order. Every chemical behavior known, reactivity, valence, bonding tendencies, flows from the arrangement of electrons in these shells. The order is strict because the Pauli principle leaves no room for duplicates. Each electron is a participant in a pattern that spans the entire atom. No internal structure drives this organization. It arises purely from the mathematical framework of quantum mechanics. The same lack of internal detail allows electrons to contribute to quantum tunneling. When faced with a barrier, a classical particle would need enough energy to climb over it. An electron, described by its wave function, has a finite probability of appearing on the other side even when it lacks the energy to cross. This is not a trick or illusion, it is a direct result of the electron's fundamental nature. The wave function extends through the barrier, and because the electron has no size, no interior, nothing to impede that extension, the phenomenon becomes possible. Tunneling is why stars ignite, why radioactive decay occurs, why scanning tunneling microscopes can image surfaces atom by atom. The simplicity also helps explain why electrons are stable. A composite particle tends to decay into smaller components when conditions allow. Electrons do not decay because there is nothing for them to unravel into. They represent the lowest energy excitation of their field. Removing an electron requires annihilating it with its antiparticle, the positron, at which point the vibration disappears and the energy transfers to photons. Until such an interaction occurs, the electron remains what it is, unchanged, unbroken, unaltered by the passage of time. As electrons weave through materials, their wave functions overlap, repel, and arrange themselves into patterns that determine how heat flows. Temperature in a solid is largely a measure of how electrons and atomic vibrations distribute energy among themselves. In metals, electrons carry much of this energy, moving rapidly and efficiently. In insulators, the responsibility shifts to lattice vibrations, since electrons remain locked into their bands. The entire field of thermal physics reflects the interplay between electrons and the environment, not any hidden mechanism within the electron. Even the architecture of biological systems arises from electronic behavior. Enzymes fold into shapes that depend on delicate electronic interactions. DNA forms its double helix because electrons in its bases stabilize specific pairings. Photosynthesis begins when a photon dislodges an electron from a chlorophyll molecule, setting off a cascade that converts sunlight into chemical energy. Nerve impulses travel because electron distributions change across membranes, opening channels that let ions flow. Life uses electrons as carriers of energy, information, and structure, relying on their fundamental consistency to keep its processes reliable. In the oldest layers of the universe, electrons shaped the formation of the first atoms. After the Big Bang cooled enough for protons and electrons to combine, neutral hydrogen emerged. Before this era, photons scattered constantly off free electrons, filling the universe with a dense fog of light. Once electrons settled into atoms, the fog cleared, allowing light to travel freely. This relic radiation, the cosmic microwave background, still stretches across the sky. The smoothness of that transition depends on the exact mass and charge of the electron. A different particle with internal structure might have introduced inconsistencies, yet observations show remarkable uniformity, suggesting that the electron's properties were fixed with precision from the beginning. Throughout cosmic history, electrons have remained steadfast, participants in every event that reshaped the universe. Their simplicity is not a constraint, but a foundation. The absence of internal layers means their behavior is entirely dictated by universal rules, and these rules remain stable across all conditions. From the smallest chemical reaction to the largest structures in the cosmos, electrons behave with absolute uniformity. Every property they show, mass, charge, spin, stability, originates not from something hidden within, but from the environment they inhabit and the laws that govern them. They are uncomplicated at their core, yet endlessly influential through the relationships they form. The more closely their behavior is examined, the more clearly they reveal a universe built from interactions rather than tiny mechanical parts. In the early universe, the behavior of electrons shaped the transition from pure energy to structured matter. As temperatures fell, electrons encountered protons often enough to bind into hydrogen. That simple act, an electron settling into the lowest energy level around a nucleus, set the stage for everything that followed. Clouds of hydrogen coalesced under gravity, igniting into stars. Those stars forged heavier elements. Supernovae spread those elements across space, and the process repeated itself through generations of stellar birth and collapse. Each step depended on the electron's unwavering identity, because the binding energies of atoms hinge on the electron's mass and charge. A slight deviation in either number would have altered the balance between gravity, pressure, and fusion, changing the fate of stars and the chemistry available to form planets. The electron's influence appears again in the cooling of the universe. As matter accumulated into galaxies, electrons played a role in radiating away heat. When electrons transitioned between energy levels, they emitted photons that allowed the gas to cool and collapse further. The ability of the universe to form stars efficiently depended on the specific ways electrons release energy. No internal mechanism inside the electron is involved in this process. It unfolds through the interaction between the electron and the electromagnetic field, a relationship so consistent that it shaped the large-scale structure of the cosmos. On Earth, the role of electrons extends to the geophysical processes that govern the planet itself. Rocks conduct heat in part through the movement of electrons. Minerals acquire magnetic signatures because of electron spins aligning during cooling. The planet's magnetic field arises from the motion of electrons and ions in its molten outer core. That magnetic field protects the atmosphere from being stripped away by solar radiation, a protective shield maintained through the behavior of particles that have no internal structure but respond to magnetic fields with perfect reliability. In human technology, every electronic device operates by controlling the movement of electrons. Transistors switch by allowing or preventing electrons from crossing tiny barriers. Lasers operate because electrons drop between energy levels, releasing light of precise frequencies. The stability of these technologies depends on the electron's stability. A particle with internal components might fluctuate or fail under varying conditions. The electron does not. It remains the same under heat, cold, pressure, acceleration, radiation, and time. The electron's consistency becomes even more apparent in experiments designed to find deviations. Precision measurements of the electron's magnetic moment involve trapping a single electron in a magnetic field and observing its behavior for months. These experiments have confirmed the predictions of quantum electrodynamics to extraordinary accuracy. If the electron had internal components, if anything inside it shifted or oscillated or aged, those changes would appear in the magnetic moment. Instead, the measurements show near-perfect agreement with theory, reinforcing the idea that the electron's properties are not emergent from an interior, but fundamental to its existence. This clarity extends into high-energy regimes. When electrons collide at immense energies, their behavior continues to match the expectations of a true point-like particle. The scattering patterns remain smooth. The energy distributions follow the equations precisely. Composite particles curve, fragment, and reveal traces of their internal makeup. Electrons do none of this. Their tracks remain thin and unbroken, Their signatures in detectors appear as sharp, bright lines with no substructure. Their absence of internal detail becomes unmistakable as energies climb. Viewed from another angle, the electron reflects the principles that hold the standard model together. Gauge symmetries, the deep mathematical relationships that govern how fields transform, define the electron's interactions. Its charge arises from one symmetry. Its coupling to the weak force arises from another. These symmetries leave no room for internal architecture. If the electron had parts, those parts would need to respect the same symmetries. They would introduce anomalies or require new fields to hold them together. No evidence suggests such structures. The consistency of the electron's behavior points to its role as a primary participant in these symmetries, not an assembly built from smaller components. All of these observations point toward an understanding that shifts perspective away from searching for what lies inside the electron and toward grasping what the electron reveals about the nature of reality. It is not a container. It is not a miniature object with internal dynamics. It is a manifestation of rules. Its properties arise from the way the electron field interacts with space-time and with other fields. The absence of internal structure is not a limitation, but a sign that the electron occupies one of the simplest possible states permitted by the universe. As deeper layers of theory are explored, such as attempts to unify all forces or describe spacetime in quantum terms, the electron continues to act as an anchor. Any new theory must reproduce the electron's behavior exactly. Its mass, charge, spin, stability, and interactions must emerge naturally from the deeper framework. If a theory predicts variations or internal components that have not been observed, the theory fails. This constraint shapes the search for new physics, guiding it toward structures that can preserve the electron's identity across all scales. Through all these layers, the simplest truth remains. The electron does not hold its properties inside itself. It carries them because the universe grants them through fields, symmetries, and interactions that exist everywhere. Its influence comes from the precision of those laws, not from anything hidden beneath its surface. In the spread of interstellar clouds, electrons guide the way atoms link into molecules that drift through cold space. Simple hydrogen combines into molecular hydrogen because electron sharing lowers the system's energy. Carbon-based molecules emerge from the same quiet interactions, forming long chains that float undisturbed for millions of years. These structures feed into protoplanetary disks, seeding the chemistry that will eventually shape worlds. The behavior of electrons in these sparse, frigid environments does not change. Their wave functions adjust to each new configuration, obeying the same rules that govern chemistry on Earth. Within dense molecular clouds, electrons influence the rate at which gas cools, the speed at which gravity can gather material, and the types of molecules stable enough to survive the collapse into a star. Even the earliest hints of organic chemistry, simple sugars, amino acid precursors, depend on electrons arranging themselves into the lowest energy bonds they can find. The electron's reliability enables this slow, expansive progression from simple hydrogen to the building blocks of life. In the warm atmospheres of young planets, electrons shape the absorption and reflection of light. Molecules gain or lose electrons in reactions triggered by sunlight, forming atmospheric layers that retain heat or release it. The stability of these reactions depends entirely on the electron's fixed mass and charge. Alter either value slightly, and the atmospheric chemistry would shift, altering the planet's temperature balance, the greenhouse effect, the formation of clouds, and the evolution of climate. Inside living cells, electrons flow through metabolic pathways with precision. Mitochondria rely on electrons moving down energy gradients, transferring their energy to pump protons and generate the molecules that power cellular processes. Photosynthesis uses electrons dislodged by sunlight to build carbohydrates from carbon dioxide and water. These electrons come from water molecules and follow a sequence of transfer steps that never deviates. Their fundamental nature ensures that each step operates with the same consistency every time. In the nervous system, electrons help maintain the electric potentials that allow signals to propagate. Ion channels regulate the movement of charged particles, and the distribution of electrons on either side of a membrane determines how easily those channels open. The flow of charge inside neurons forms patterns that encode memory, perception, attention, and thought. The electron remains the same particle in every one of these moments, carrying out its role effortlessly because the laws governing it do not drift. In materials under mechanical stress, electrons redistribute themselves as bonds stretch, compress, or rotate. The resilience of a material, its ability to bend without breaking, to absorb force, to return to its original shape, depends on how electrons respond to these distortions. Metals exhibit ductility because electrons form a kind of shared pool that allows atoms to slide past one another without losing cohesion. Ceramics resist compression because electrons lock their atoms into rigid directional bonds. Polymers flex because electrons in their long chains form bonds that can twist and shift without snapping. In extreme heat, electrons break free from atoms, creating plasmas that behave like fluid seas of charged particles. These plasmas generate magnetic fields as they swirl, forming structures that appear in solar flares, auroras, and fusion reactors. The electron's presence in a plasma reveals its ability to participate in collective behavior without losing its identity. Despite the chaos, its charge, mass, and spin remain unchanged, guiding the flow of currents and the emission of radiation. In the cold vacuum of space, a lone electron carries its properties exactly as it would under immense pressure or intense heat. The universe treats it the same everywhere. No sign appears that different conditions coax hidden components into view. No resonance emerges to suggest internal vibrations. Every experiment confirms the same clean signature. This universality turns the electron into a kind of reference point. Whenever the fabric of physics is tested, the electron provides one of the most sensitive indicators of any deviation. If space-time had subtle imperfections, if new forces existed at small scales, if hidden dimensions influenced particle behavior, the electron's interactions would reveal a trace. Precision measurements search for these traces relentlessly. The absence of anomalies strengthens the conclusion that the electron is as fundamental as current understanding allows. The deeper theories that attempt to unify gravity with quantum mechanics respect this constraint. Whether through quantum gravity, loop formulations, or string-based descriptions, any proposed framework must allow the electron to emerge with its observed properties intact. The consistency of these properties becomes a boundary condition for the shape of any future physics. Through all the environments it inhabits, interstellar clouds, planetary atmospheres, living cells, metals, plasmas, vacuum, the electron remains unchanged. Its universality allows matter to remain coherent across space and time. This constancy is one of the reasons the universe behaves in an ordered way, rather than dissolving into chaos. A particle with internal structure would likely exhibit variations under stress, revealing seams or fractures. The electron offers no such hints. Its nature is precise, stable, and uniform. This stability carries through the entire timeline of the cosmos. Electrons present today are indistinguishable from electrons that formed in the first moments after the Big Bang. They have not aged, degraded, or evolved. They have carried their properties through billions of years without deviation. The ordinary world, with all its complexity, rests on the quiet reliability of a particle that behaves as though it was defined once and for all by the early universe, with no inner parts to shift or fail. In laboratory experiments, the electron's remarkable consistency becomes even more visible. When beams of electrons pass through crystal lattices, the resulting diffraction patterns form precise arrangements of bright and dark regions. These patterns reflect the wave nature of the electron, revealing the exact spacing between planes of atoms. Repeating the experiment with different crystals produces new patterns, but the electron's behavior remains unchanged. It molds itself to the structure before it, adapting its wave function without ever altering the properties it carries. In precision spectrometers, the electron's charge is measured with exquisite care. A small imbalance would ripple into countless processes, distorting the structure of atoms and the stability of matter. Yet measurements always return the same value. Devices built decades apart, using different techniques, on opposite sides of the planet, converge on identical results. No variation appears. This unity across time and method reflects the electron's role as a fundamental anchor in the landscape of particle physics. Inside Penning traps, single electrons can be held in magnetic fields for months. Their motion reveals their magnetic moment with extraordinary detail. The measured values align almost perfectly with theoretical predictions, confirming the structure of quantum electrodynamics with a precision unmatched by any other relationship in physics. The agreement shows that the vacuum fluctuations surrounding the electron behave consistently in every experiment. If the electron had internal components, or if the vacuum responded inconsistently, these values would drift. They do not. In materials research, electrons reveal another facet of their simplicity. Scanning tunneling microscopes rely on electrons tunneling between a sharp metallic tip and a surface only a few atoms away. This tunneling current responds sensitively to the distance and structure of the surface, enabling images that map individual atoms. The clarity of these images depends on the electron's ability to behave exactly the same way in every instance. Its point-like nature allows the tunneling process to respond solely to the geometry of the surface, without interference from any hidden internal structure. In astrophysics, electrons emit synchrotron radiation when accelerated in magnetic fields. This radiation produces bright arcs around pulsars and jets around black holes. The radiation's spectrum follows precise mathematical forms that match the predictions of quantum theory. These distant signals show that electrons behave the same way under conditions far beyond the reach of Earth-based experiments. Even when flung through magnetic fields, trillions of times stronger than anything created in a laboratory, the electron's response follows the same rules. In cosmic rays, electrons racing through space at nearly the speed of light strike detectors with energies measured in billions of electron volts. Their tracks remain sharp, narrow, and consistent with point-like behavior. When these particles interact with magnetic fields in the galaxy, their paths bend gently according to the same equations that describe an electron in a simple laboratory magnet. The behavior carries no signature of an interior, no sign that the particle hides anything beneath its surface. In theories that attempt to unify all known forces, the electron occupies a special place. Grand, unified theories describe how quarks and leptons might emerge from deeper symmetries at unimaginable energies. These theories require that electrons remain stable and featureless at accessible energies. Any internal structure would distort the unification patterns. The electron's observed behavior provides strict constraints that any deeper theory must satisfy. Its simplicity is not an afterthought. It is a cornerstone in the architecture of possible unification. In quantum field theory, the electron's existence is tied directly to the structure of the Lagrangian that defines the Standard Model. The terms governing electrons express the symmetry of the underlying gauge groups. No internal parts are required to generate spin, charge, or mass. These properties arise from interactions with fields that pervade space. Mass comes from the Higgs field. Charge comes from the structure of the electromagnetic field. Spin arises from the form of the electron's wave function. Everything essential to the electron's nature resides in the laws of physics, not inside the particle. In the mathematics of renormalization, the electron's properties evolve with energy scale, revealing how interactions shift subtly in different environments. Yet the particle itself remains elementary. The renormalization group flows show how charge and mass are dressed by the vacuum, not by internal components. The closer the flow is examined, the clearer the distinction becomes. The electron is fundamental, while the environment contributes the surrounding complexity. The role of the vacuum grows more significant the deeper this picture is explored. The vacuum is not empty. It is structured, seething with temporary excitations of all fields at once. The electron moves through this environment like a small, clean signal passing through a noisy medium. The vacuum modifies its behavior, but it does so in ways that are completely predicted by quantum theory. The patterns of vacuum polarization and self-energy corrections emerge without requiring the electron to have any internal structure at all. This interplay between particle and vacuum becomes most striking in the context of the anomalous magnetic moment. The slight difference between the electron's magnetic moment and the value expected from a simple spinning charge arises from the influence of virtual particles. These effects match the predictions of quantum electrodynamics to more than 10 decimal places. Nothing in the measurement hints at additional layers hidden inside the electron. Instead, the agreement shows how deeply the electron's properties are tied to the structure of the vacuum itself. In the broad sweep of physics, the electron remains one of the most thoroughly examined entities in the universe. Across scales ranging from subatomic to cosmic, across environments from absolute zero to the hearts of stars, its behavior never suggests complexity beneath the surface. Every phenomenon that might appear to require a layered particle emerges instead from fields, symmetries, and interactions. The more the electron is studied, the more its role resembles that of a fundamental note in the composition of reality. It carries no internal machinery, no compartments, no seams. It acts as a point-like excitation of a field woven into the fabric of the universe, participating in every structure that matter forms. Its simplicity enables the complexity around it, and its stability anchors the laws that shape both the familiar world and the distant cosmos. In condensed matter systems pushed to their limits, electrons display behaviors that can feel almost paradoxical. Yet each one reinforces the same conclusion. A simple particle can generate intricate phenomena when placed in the right environment. In quantum wells and quantum dots, structures only a few nanometers across, electrons become confined in ways that quantize their allowed positions. The confinement does not reshape the electron itself. It reshapes the space around it. The electron's wave function adjusts, forming discrete energy levels reminiscent of miniature atoms built not from protons and neutrons, but from potential wells engineered by human hands. In topological materials, electrons respond to the arrangement of atoms in ways that reveal hidden geometric structures in their wave functions. Some materials allow electrons to travel along edges without scattering, immune to impurities and defects. Others produce quasi-particles that move as if they carry a fraction of an electron's charge. These emergent excitations are not evidence of internal layers inside the electron. They arise from collective behaviors involving countless electrons at once, forming patterns that mimic new particles. The electron remains fundamental, while the system around it creates illusions of complexity. In superconductors, cooled to extreme temperatures, electrons form paired states that glide through a lattice without resistance. These Cooper pairs act as single quantum entities, their coherence stretching across macroscopic distances. The paired state relies on interactions with lattice vibrations, not on any internal structure. The electron simply participates in the pattern because the environment permits it. The resulting current can persist for years without weakening, a macroscopic expression of the electron's capacity to fit seamlessly into collective order. In the interplay with photons, electrons reveal yet another facet of their behavior. When struck by light, electrons absorb just enough energy to shift into higher states, never more and never less. The precision of these transitions produces the spectral fingerprints used to identify elements across the universe. Astronomers can examine the light from stars thousands of light years away and determine which atoms sit in their atmospheres, because electrons follow the same rules everywhere. Their behavior is not influenced by internal components. It is governed entirely by the structure of the atom and the fields acting upon it. In the presence of strong gravitational fields, electrons experience time differently depending on their position. General relativity predicts that clocks run slower in deeper gravitational wells, and electrons reflect this in their energy levels. Atoms closer to massive bodies emit light at slightly different frequencies than identical atoms in weaker gravitational fields. This gravitational redshift depends on the electron's mass and the nature of its bound states. Nothing about gravity reveals an interior to the electron. It simply modulates the space-time in which the electron's wave function resides. In particle detectors, electrons show their identity with unyielding clarity. When a high-energy photon strikes a nucleus, it can convert into an electron-positron pair. The pair emerges with properties that exactly match those of electrons and positrons produced in any other way. Same mass, same charge magnitude, same spin, same behavior in magnetic fields. The consistency across all production mechanisms emphasizes that the electron's nature is not tied to its history or origin. A particle with internal structure would be more likely to reveal irregularities depending on the conditions of its creation. The electron does not. In neutron decay, a neutron transforms into a proton, an electron, and an antineutrino. This process relies on the weak nuclear force. Yet, the electron produced carries the same properties as any other electron in the universe. It does not matter whether the electron emerges from a decaying neutron, a cosmic ray collision, a laser-driven experiment, or the interactions inside a star. The identity remains perfect. The weak force does not assemble the electron from smaller pieces. It simply shifts the configuration of fields, allowing an electron-shaped vibration to appear. In the plasma of a fusion reactor, electrons move freely among nuclei, guiding the behavior of the hot, charged gas. The stability of the plasma depends on how electrons respond to magnetic confinement, how they transfer energy, and how they interact with the ions around them. Plasma instabilities often arise from collective motions of electrons. Yet, these instabilities never suggest that the particles themselves have internal layers. Instead, the instabilities reflect the delicate balance of fields guiding their motion. In the search for dark matter, electrons serve as sensitive probes. Some detectors rely on the faintest flicker of energy deposited when the hypothetical dark matter particles interact with electrons. The precision of these detectors depends on the electron's exact response to energy transfers. Any deviation in its behavior could hint at new physics. So far, electrons continue to behave exactly as predicted, offering no sign of internal complexity or hidden ingredients that might distort these interactions. In metrology, the electron defines fundamental constants. The fine structure constant, one of the most important numbers in physics, describes the strength of the electromagnetic interaction. This constant governs how electrons interact with photons, shaping atomic spectra and the stability of matter. Its value emerges from the structure of quantum electrodynamics and the electron's role within it. If the electron contained smaller pieces, the value might vary with energy or environment. Precision tests show no such variation. In the broader theoretical landscape, electrons occupy a minimalistic role. They fit neatly into the representations of gauge groups that define the Standard Model. Their behavior matches the patterns predicted by quantum field theory, without requiring correction terms for internal dynamics. The elegance of this match supports the view that electrons are as fundamental as the mathematical framework suggests. In every domain, cosmic, atomic, biological, technological, the electron's simplicity is not a constraint, but a strength. The absence of internal structure allows its properties to remain uniform across all conditions, anchoring the laws of physics with a stability that makes the complexity of matter possible. Across every scale the universe allows, the electron remains unchanged. It carries no layers to peel back, no inner landscape waiting to be revealed, no hidden machinery driving its behavior. Its nature flows entirely from the fields that fill space and the symmetries those fields obey. That simplicity holds the fabric of matter together with a precision that leaves no gaps. Atoms form because electrons settle into stable wave patterns. Molecules take shape because those waves combine and reshape around nuclei. Stars burn because electrons guide the conditions under which fusion ignites. Life rises from patterns of charge, bonds, and currents that flow with unwavering consistency. The world does not rely on complicated building blocks. It relies on fundamental notes that remain steady everywhere. The electron is one of those notes, persistent and exact, carrying the same identity from the first moments of the universe to the present moment within your own body. Everything built on top of it, the structures of matter, the processes of life, the light of stars, draws its reliability from a particle that never changes its tune. The deepest investigations of physics circle back to this same point of stillness. Nothing inside the electron explains its influence. Nothing beneath it has been found to shape its form. It stands as a direct expression of the rules that govern reality, a clear and continuous signature of the universe's underlying order. Through that clarity, the electron becomes not a puzzle to open, but a reminder that simplicity at the foundation can generate boundless complexity above it. Its presence threads through the cosmos without aging or drifting, the same in ancient starlight as it is in the quiet structures of the world around you. A single particle with no interior, yet capable of shaping the entire visible universe through the grace of the laws that define it.